Hello everyone, welcome back to the channel. Today we're going to be doing a deep dive into phylogenetics, and we're going to really focus in on how phylogenetics can be used to date the divergence between two organisms. Now, I was inspired to do this video many months ago when I first started imbibing creationist content because this one particular creationist, who shall remain nameless, consistently calls phylogenies just lines on paper, right? You've all probably heard this many times. And as someone with a phylogenetics background, this really kind of ground my gears. But I thought, you know what, to get into this, to really answer this question thoroughly would take so much time. Nobody's going to really want to watch this. And you know what? I decided to hell with it. I'm going to do it anyways. I'm going to explain to you in depth how we estimate phylogenies and how we do divergence time dating, because I'm just so sick of hearing this argument. So next time you hear him say this, you can refer him to this video, or at least tell people in the comments that there is a lot more to phylogenetics than they understand, and it is not just something we dreamt up, just something we stand around drawing lines, that it's actually a rigorous statistical methodology that is far more complicated than this particular creationist could even begin to understand. So we're going to answer the question in this video: are phylogenies just lines on paper? And we're going to answer this first by saying, how are they actually built? And how do we use them to determine how long ago two organisms diverged from each other? Now, the way that I want to do this is in a tiered approach, because I really want everybody watching this video to take something away from it, right? And so first, we're going to do a very simple primer. We're going to start off assuming you know absolutely nothing about phylogenetics, how phylogenies are built, anything like that. If you're coming in completely fresh with no background knowledge, this tier is for you. This should prime you to sort of be able to follow the next two tiers. If you do have some phylogenetic background, or you do have some understanding, this might be like a very simple thing that you can just kind of gloss over. Tier 2 is going to be a little bit more advanced. We're going to be talking about things like substitution models, and we're going to introduce the idea of fossil calibrations. This one is going to have a little bit more math. The first one, we basically do no math. We're going to add a little bit more math in the second one. And then in the third one, we're going to do an advanced walkthrough. So this is where we are really going to take this unnamed creationist to task and show him that phylogenetics is a rigorous statistical methodology. That it's a methodology derived from statistical hypothesis testing, and that it is not just drawing lines on paper. And we're going to do this by showing how we actually estimate ancestral nodes using both a likelihood and a Bayesian approach. And we're going to show how Bayesian phylogenetics actually works using Markov chain Monte Carlo estimation of model parameters. If none of that makes any sense to you, if that just sounded like I was speaking a different language, don't worry. I'm going to explain all of it in detail. But just know that tier 3 is going to be the most advanced of these. There's going to be a lot of math. I'm going to explain it, so don't be afraid. I'm going to like walk you through it, but it will be significantly more advanced than the first two. So yeah, with that, let's dive on in. Let's start off with tier 1, and let's give a very simple primer of phylogenies, and how we construct them and how we can use them to estimate when organisms diverge from each other. Okay, so for this example, we're going to assume a couple of things. One, we're going to assume that this black phylogeny that I've shown here is the real phylogeny, right? So we're not estimating it. It is an actual phylogeny that we know exists. And then across each one of the colored individuals, these are our samples, okay? So we sampled some individuals, and we want to know how are they related to each other. Now, we don't know what that real phylogeny is in nature, right? We're trying to estimate it, but for our purposes here, let's say this is the real phylogeny, so that we can kind of help understand how the data itself gets generated given that phylogeny, okay? So the currency of phylogenetics, what we actually have, what the data actually looks like, are mutations. Now, we need to understand something about how the mutational process works given an underlying phylogeny, an underlying relationship among these individuals. So for this data set, these two, the green and the blue, are the most related individuals. That means they share an ancestor most recently in the past. The purple individual here diverged first. They have the longest branch that they do not share with anyone else in the data set. The length of these branches are very, very important, and they tell us something about the probability that some mutation has occurred along that branch. The longer the branch is, which you can think about as time, the longer time has been between our sampled individual and the time that they have a common ancestor with the rest of the samples, how long that is, gives you some estimate of how many mutations could have occurred along that branch. So let's put some mutations on this tree. So these red stars represent the mutations. Now, as you can see, since this is the longest branch, it has the most mutations on it. That means that this purple individual has all of these mutations that are unique to them relative to everyone else in the data set. No one else in the data set have these mutations, okay? Everyone else in the data set have some mutations that are shared across them. To see the mutations that are shared across, we look at the internode mutations. Okay, so this is the common ancestor of our data set. This is the common ancestor of all these individuals in the data set. Notice that this mutation occurred before this common ancestor. What that means is that all of these individuals share that mutation. Okay, so anytime you see a mutation in the internode, that means everybody that descends from that ancestor has that mutation. So it's shared across that data set. Okay, so we can see that there is three mutations that are shared across the data set. And then along these branches are the mutations that are unique to individuals. Now, given that we have that sort of understanding about the probability of the number of unique mutations occurring and how mutations can be shared across individuals, we can begin to sort of get an idea of how we could reconstruct this tree, assuming we didn't actually know what the tree structure is. And we can do this simplistically by building a table. So we can ask, okay, across our data set, how many mutations are unique, right, are not shared with anyone else in the data set? And that tells us how recently they diverge from any other individual in the data set, right? So remember, since these two individuals, the green and the blue, are the most related, they separated the most recently in the past, they should have the fewest number of mutations that are unique to them relative to anyone else in the data set, right? Because their ancestor was very, very recently. And so indeed, what we see is that that only one of them has any mutations that are unique, and blue has no mutations that are unique. The next one, given that this underlying tree structure is red, they should have the next most number of unique mutations. And sure enough, they have 2 mutations that are unique to them relative to anyone else in the data set. Since purple is our outgroup, is our most distantly related individual, as I said before, they should have the most number of unique mutations, given that they diverge from everyone else in the data set much further into the past, okay? And sure enough, they have 5 mutations that are unique to them. So that gives us some idea about how we can begin to think about the number of mutations per lineage telling us something about time. How long ago did any individual diverge from anyone else? Now, what we also need to be able to do is reconstruct the tree structure itself. Right, so the number of unique mutations tells us something about the branch length, but how can we actually get the topology? That is to say that green and blue are most related, with red as out to them, yellow as out to them, etc. How do we get that structure? To get that structure, we need to consider the mutations that are shared among the data set. So since purple shares no mutations with the data set, we know that purple is the most diverged. Right, they have nothing that groups them with the rest of the data set, so we would put them as sort of the out group, right? No, they have no shared mutations, and they have the most unique mutations. So that tells us they are the out group. Next, we see that there's one mutation that is shared across green, blue, red, and yellow. That's this mutation here, right? That mutation is shared across all 4 of those individuals. Right? So that tells us that those 4 individuals are more related to each other than they are to purple, right? Because purple has no shared with any of the rest of them. Next, we see that there's another mutation, this one here, that relates red, blue, and green that is not shared with yellow. That means that red, blue, and green represent a clade with yellow as out to them, because yellow does not have that mutation. Finally, we see that blue and green have a unique mutation that is not shared with red. That means blue and green are most related with red as the outgroup. So in this way, we've seen that shared mutations allow us to reconstruct the topology of the tree, the branching order of the tree, whereas the number of unique mutations tells us how long those branches are to each one of those individual nodes. Now, the next thing that we can do is actually convert this table into a pairwise difference table, right? You can also think about this as a pairwise divergence table. All I've done here is just made this pairwise matrix. So it's green and greens compared here, green and blue, green and red. So you just read this as a pairwise comparison. I've just put zeros along the diagonal because we're only interested in divergence between. And then all I did is counted the number of differences between each one of them, right? So between green and blue, there's one difference. That's that difference there. Between green and red, there are 4 differences. So that's 1, 2, 3, 4, right? 4 differences. Green and yellow, there are 7 differences. 1, 2, 3, 4, 5, 6, 7. Remember, you have to read both. You have to go both sides of the tree, right? That tells you how many differences there are is if you read both through both branches, and then you can do this across the entire data set. Now that we know how many differences there are between each individual, we can start to get an estimate of how long ago those individuals diverge from each other. So let's assume that we estimate a mutation rate, right? Like we have some pedigrees and we estimate father, mother, child, and there's some number of mutations that they are inherited across those lineages, and we can get an estimate of the mutation rate, right? In a very simplistic way. And let's say we estimate the rate as 1 mutation every 20 years. Okay, so we've not only have we taken the per generation, we've converted it to a yearly mutation rate, 1 mutation every 20 years. So then what we do is just go across our divergence table and multiply that number by 20. Okay, so what that does is that takes the absolute number of differences, multiplies it by the number of years we expect it to take to get that number of differences, and then that gives us the divergence time between each individual. Okay, so we've just now converted this out. So what this means is that between green and blue, there's a 20-year difference because there's 1 mutation between them. From green and red, there's 80 years that separates them. From green and yellow, there's 140 years, et cetera, et cetera. So one of the things I want to draw your attention to is that purple share an ancestor at the exact same time with all the rest of these groups, right? And that's this ancestor here was the last time that they were related. But notice that there's a range of years that this ancestor could have existed at, from 160 up to 200 years. There's a range, right? How does this happen? Well, remember that mutations are stochastic, right? The probability that they occur is not absolute. They're not constant, right? There's some stochasticity in them occurring. What this means is that we don't actually expect mutations should be a direct translation to time. They are a relative translation to time, given that mutations occur stochastically by chance. So the way we often will represent this is by giving a confidence interval, right? So if we go down here to this last common ancestor, just focus on this part here, we take our 4 dates, 180, 160, 180, 200, and then divide it by 4. So we take an average, and that average is 180 years plus or minus 20 years. Now, oftentimes, if you've ever seen a phylogeny, you see these like confidence intervals around the nodes. That's what's happening. Right? They're saying this is our mean estimate with some range around that estimate. Because again, the mutational process is not absolutely constant, it is stochastic, okay? So just by chance, the exact same distance between 2 individuals will have more mutations than there is in a distance between 2 other individuals that may only have a couple of mutations, despite the fact that the rate of mutation is roughly the same across all, okay? And then we just do this for each and every node, and that gives us the final node at 180 years, the next node up at 133, the next at 70 years, and the most recent at 20 years. So in this very simple kind of example, we've reconstructed the tree. We've had some idea about how it's reconstructed by shared patterns of variation, and how long branches are by the number of mutations that are unique to each one of the tips in that branch. And then we've also shown how we can convert those unique number of mutations into absolute time using some underlying mutation rate. Okay, so that's the tier one explanation. Hopefully now you have some very, very basic idea about how phylogenies are built. For the tier two, what I want to do is actually kind of attack our simple model. Um, and I want you to take a second and try to think about, before I actually show you, what were some of the assumptions of this very, very simple example. There were actually a ton of assumptions that we made to do those calculations. And so what this tier two is going to represent is taking all of those assumptions and explaining them to you in a more nuanced way so that you can understand how we really do it. Okay. We don't really do it in the way I just showed you. That's the point I want to make clear here. That very, very simple way was just to get the idea across. That's not actually how we build phylogenies. Okay. That's a very simple, very cartoonish, simple way. So what's one assumption that we made? Well, first, we assumed that the rate of substituting any one nucleotide for any other nucleotide is exactly equal. Okay, so the probability or the rate of change from an A to a T is exactly the same as an A to a G or a C to a T, right? That all of those changes are exactly the same. That is to say, we didn't have to worry about what kinds of mutations were occurring. We just pretended that they were all exactly equal to one another. We're going to talk about why that's very rarely true, but we're also going to talk about when we could know that it could potentially be true. Second, we assume that all sites were equivalent. That is to say that regardless of which site gets mutated, we're just treating them all as equal to one another, right? So the rate of change at one site is exactly equal to the rate of change at another site. We know that is not true. There are things called mutational hotspots that violate that assumption, and we're going to talk about that. Third is that we assume that the yearly mutation rate equals the substitution rate, right? We took some pedigree estimated yearly rate, and then we just converted that into absolute time. There are a ton of reasons why that is a very simplistic assumption that is very often violated, and we're going to talk about why that is and how we account for it. Now what I want to do is then go from those assumptions to ask, can we get an absolute time without relying on the yearly mutation rate, right? Without having to make this assumption, can we actually get the true substitution rate in terms of absolute time? Let's start with talking about models of substitution, right? So the model that we first showed was assuming equal rates, right? That's our first assumption. And this is a model. It's called the Jukes-Cantor model. Often will be abbreviated to JC69 from the Jukes-Cantor paper in 1969, where they just assumed an equality of rates. So what I'm showing you here is a matrix. This is the probability of rate change for any given nucleotide to any other nucleotide. And this is that matrix. So A, T, C, and G across the top. It's assumed A, T, C, and G along the column as well. So what the diagonal represents is the probability of basically staying the same. I just standardized that to 1 because we're really only interested in actual changes, not in remaining the same. We'll change that assumption shortly, but for right now, we just assume we're just going to standardize it to 1. So what we really care about is, let's say, the rate of a change from an A to a T. That rate is alpha. A to a C, alpha. A to a G, alpha, right? It's a constant rate. We're assuming one value can represent the rate across all possible changes. Therefore, the probability of changing from one nucleotide to any other nucleotide is exactly the same. It's just alpha over 3. Okay. Now, this makes a very specific prediction that allows us to know whether or not this model is accurate, whether or not we can actually use this model for a given nucleotide region. Okay, because it predicts the equality of base frequencies. Let me explain what that means. So let's say you have 10,000 base pairs. You sequence one 10,000 base pair region, and across that region, you can calculate the frequency of A's, T's, C's, and G's. Okay. If that region has evolved under a Jukes-Cantor model, under a model in which any possible change, any possible rate is exactly equal, at equilibrium, the frequencies of each given nucleotide should be exactly the same. They should be 25%. So if you sequence a region and you find 25% of the nucleotides in that region are A's, 25% are T's, C's, and G's, then you can use a Jukes-Cantor model. A Jukes-Cantor model well represents that region. We very rarely find that. It's far more often it is skewed in one direction or another. So for most of the time across the genome, we don't use Juke scanner models. There are some regions where the Juke scanner works just fine, but again, not very many of them. We usually have to use a little bit more complex of a substitution model. So the next step up from the Jukes Cantor is the Kimura 1981 model. This is often, you might see this called the K2P model. It's Kimura 2-parameter, or K81 model for Kimura 1981. There's a bunch of different names. Point being is that the Kimura model assumes that there's 2 parameters. That's why it's the 2-parameter model. And the 2 different parameters emerge because of different rates between transitions and transversions. So we need to know what that is. So a transition is changing a purine to a purine, or a pyrimidine to a pyrimidine, right? To remember what those are, A's and G's are purines, C's and T's are pyrimidines. When I was in graduate school, I went to Texas A&M, which are the Aggies, and the way we were told to explain it to students to help them remember the difference is that Ags are pure. I know that's absolutely silly, but for some reason, it actually helped me keep it straight in my head. So AG are purines, then C's and T's are pyrimidines, okay? I don't know if that helps you or not, but it helped me. So an A to a T, that change is beta. So beta is now going to represent transversions, and then where's my cursor? Then a C to a T, which is this change here, is alpha, and that represents a transition, right? Because it's a pyrimidine to a pyrimidine. So what you can notice is this matrix has a diagonal of transitions that is nestled within betas, which are transversions, okay? From that, we can then estimate that the rate of change, kappa, should be equal to alpha plus 2 beta. It's 2 beta because there's twice as many possible transversions as there are transitions. Now, really interestingly, that means that we should, assuming equality, actually see twice as many transversions as we do transitions. But we don't, right? Alpha is actually still typically greater than beta because transitions just occur like molecularly, they occur easily more often than we see transversions. So this model actually does a pretty good job in a broad swath of the genome, especially if the genome is generally evolving neutrally. This particular model does a really good job. But again, we don't even have to assume this simple model. We can make an even more complex model. So the most complex model is called the general time reversible, or GTR model. This model assumes that every possible change has its own rate, that there is no assumption of an equality of rates across each of this matrix. So for an A to a T, or here, for this one, this is a T to an A, it has its own rate. For a C to an A, it has its own rate. G to an A has its own rate. Every possible change has its own rate. Furthermore, we can now parameterize across the diagonal as the rate at which you don't change, right? So we often call this the invariant rate. So the rate of just staying exactly the same as these particular values, right? So the GTR allows us to estimate change as an independent process with its own rate, including the probability of no change, which is the invariant rate. This is the model that more often than not, you're going to see applied in phylogenetics. We very rarely use the Kimura 2-parameter, very rarely use Jukes Cantor. This is the model we almost always use. It's the most complex and it's the most computationally costly, but it's also the most realistic. Okay, all of that's cool. Now we have some idea about substitution models, but we're still being a little too simple, right? We're still assuming that across every single site, that model works, right? That we're still assuming at some level that rate is constant across sites. But it very rarely is. Again, as we already mentioned, there are such things as mutational hotspots where you get a lot more mutation. So I've showed this up here at the top. So you've got the substitution rate on the y-axis and then the base position on the x. So A, T, C, G, T, 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 A, where the G and the T are landing in a mutational hotspot. So at that spot, you see far more mutations than you do at the surrounding locations. Because of this, we actually want a model that allows that rate to vary by site, not just by the specific nucleotide at that site. We can do that too. So let's take our GTR model, which is shown right down here, and let's add this additional parameter that we generally call gamma. So what you often see this as GTR plus gamma. Now what the gamma represents is that as you go to each and every site, you're going to draw the rate parameter from a distribution, and that distribution is gamma distributed. Now gamma distributions have shape parameters that are determined by alpha and beta, and so right here I'm showing you different shapes of that gamma distribution given different values of alpha and beta. So what this does is this allows us to account for the fact that at every single site, you can have an independent rate, a rate that is driven not simply constant across sites, but that may be driven by mutational hotspots or cold spots. So this is just another way that we can account for this variation in rate and add a little bit more realism into our models. Okay, so the next assumption that we made is that the mutation rate was equal to the substitution rate. I'm showing that up here at the top. This was a famous equation that is very often attributed to Moto Kimura, but it has been recently pointed out to me that Sewell Wright actually derived this in 1938. So this is a screenshot here at the bottom from Wright's paper in 1938. Notice here that the W bar represents selection, V is the mutation rate, and K is the rate of evolution. Notice that he says if there is no selection, W bar equals 1, K equals V, which means that he derived this mutation substitution rate equivalency when there is no selection in 1938, almost 30 years before Kimura. I didn't know, this was just recently pointed out to me, and I thought that was really, really cool, so I wanted to share it. Now, he didn't think that this was a thing that occurred very often. This was just like a throwaway line that he had. So he didn't like develop it any further. That's why we generally attribute it to Kimura, because Kimura is the one that actually like took it and ran with it, right? But I just wanted to point out to you that it was actually Wright that very first derived this. That was a bit of an aside, but I really like PopGen history, and I wanted to share that. So basically, the mutation rate equals the substitution rate in a very select environment. And let's talk about what that environment is. So first, it relies on several key assumptions. One is that population size is constant through time. And we can see that in this equation. So N of E, for these two to cancel and equal mu, this rate has to be a constant. N of E must be a constant through time. If N of E is not a constant, they don't cancel. Right? Like they're not equivalent, and you can't actually cancel those values. So population size matters. The substitution rate doesn't equal the mutation rate. Two, it assumes that populations are homogeneously distributed. Again, that's assuming that N of E is constant not through time, but across space. Okay, so N of E, for example, could be averaged out and to be constant across time, but if at any time slice it varies across the landscape, then the rate of drift, that 1/2NE, is not equal for all positions in the landscape. Again, meaning you can't cancel those values and population size matters. Finally, it assumes that there's no selection at all. So this is very important. Pedigree mutation rates don't assume selection. Right, you're getting the mutation rate immediately from parent offspring sequencing, right? What you haven't seen there is purifying selection, because that offspring has not, maybe that offspring will have no offspring of their own, right? You don't know, like that you don't follow it down the line. So you're just getting the absolute number of mutations. What you're not getting is post-selection number of mutations. So again, this equivalency holds under strict neutrality, assuming there's no population size variation through time or across space, and assuming that there has been no selection at all. Now, while this might seem incredibly restrictive, it does hold for some parts of the genome for some populations. To make this equivalency, it just means that you need to know something about the life history of that organism, okay? You need to actually do some investigation to understand whether these assumptions hold. Because if they don't hold, then you can't make this very simple model, and you need to do something a little bit more complicated. This is, again, not to say that it's intractable. We have tons of models that can do this. It's just something that we need to understand, that we need to recognize when we start doing phylogenetics. Okay, so this then leads to a question then: how well can we model substitution rates? Importantly, molecular clocks don't actually rely on this equivalency. It's often like misconstrued by both creationists and even people that like don't do phylogenetics. They often will say like, well, the molecular clock means that you have to have a constant mutation rate, therefore you have a constant. No, no, no. It doesn't actually rely on that. What it relies on is that substitution rates are relatively constant. The mutation rate doesn't have to equal the substitution rate for the substitution rate to be constant. Okay, because again, those things can be decoupled across evolutionary time. So the way that we generally model substitution process is as a Poisson process. A Poisson process is represented by this little diagram here at the bottom. You can imagine it as having some starting initial state. Let's say it's an A. Let's say A is your initial state. Then from time point 1 to time point 2, or from state 1 to state 2, this could be a generation. This could be a replication cycle. This could be any unit of time that you're interested in. From state 1 to state 2, there's some probability that between those two states a mutation happens. And in this case, we mean a substitution happens. So an A goes to a T with some mean probability that's determined by the rate parameter that we're showing here, which is just lambda, multiplied by time, by the interval of time between those two states. Okay, so you can think the greater that interval of time is, the more chance you have for a substitution to occur. Now, importantly, for the molecular clock model to hold, and for like the Poisson process to actually represent what we think it does, to actually be representative of sort of a constant substitution rate, the mean equals the variance. So in a Poisson process, the mean, which is lambda times t, is exactly equal to the variance in that rate, which is lambda times t. However, evolutionary rates are variable across loci and taxa. This goes all the way back to John Gillespie, who was a pretty fervent critic of Moto Kimura. They had lots of back and forths. And what Gillespie actually showed is that the variance in the substitution rate doesn't actually equal the mean of the variance. What this means is that it's unlikely to be well captured by a strict Poisson process. Another way to think about this is that the variance is non-normal. Okay, it's super variable across different taxa and across different loci. There's lots of reasons for this, and that we've already kind of talked about them. One is that populations aren't constant; they're variable. Variation in the size of the population. So if you have booms and busts in your population size, that is going to speed up and slow down the substitution rate, right? And so the variance, especially if those boom and bust cycles aren't constant, right? If you have this like random boom and bust cycles, then what you're going to find is that your variance doesn't capture the mean rate at all, right? It diverges very strongly from the mean rate. So there's lots of things that can influence the variance in the evolutionary rate across loci. And so our models need to be able to account for this, which means that we can't assume the equality of mean or the equality of rate in evolutionary change across different branches, which again was one of those simplistic assumptions that we made in our early model. Okay, so the last thing I want to talk about in our sort of tier 2 is the incorporating fossils. So I've kind of built up that mutation rates are a pretty unreliable source for substitution rates on their own. Just like standing on their own, they're pretty unreliable. However, we can incorporate fossils and greatly improve the rate estimation, because what fossils allow us to do is calibrate the molecular clock, right? It allows us to actually set the molecular clock to absolute time. And we can do this because we can date when fossils are found. So if we go back into the fossil record and we find a particular fossil at this point in time, we know that that fossil must have existed, that lineage of that fossil must have existed at this point in time. Now, if that fossil represents the ancestor of an entire clade, then we can calibrate the rate of change across that clade given that fossil. We don't make it constant, as I'll explain a little bit later. We actually kind of put a distribution of ages given that fossil. So all fossils don't have like an exact date. We give them a range. So we apply that range, usually with a hard young age, but with a very soft old age, so that it can be a broad range of age estimates. But what it does allow us to do is calibrate that substitution rate. which greatly improves our ability to actually estimate the rate if we have some external sources that we can use to do that rate estimation. It's not always just done with fossils. You can also do this with biogeographic events. So for example, one of the things I did in graduate school is I didn't have a lot of fossils for amphipods, especially for the group that I worked on. But what we do have is a very good estimate of when the Florida Peninsula arose, right? The Florida Peninsula hasn't always been there. It's a relatively recent emergence. And so what you can do is that since amphipod populations are diverged on either side of the Florida Peninsula, we can actually calibrate that divergence as being no younger than the emergence of the Florida Peninsula. And so we can do things like that to calibrate the molecular clock and allow us to get an external verification to our rate estimations. Okay, now we've gone through the first two tiers. We explained very simply how mutations emerge on phylogenies, how we use those patterns of shared variation and unique variation to estimate the topology of the tree and the time of divergence between organisms. From there, we went into tier 2, where we kind of dissected our little simple example, talked about all the little holes in our simple example, and then provided some ways in which we could begin to think about accounting for those things, talking about substitution rate models, as well as possibly incorporating fossils into our phylogenies. Now in tier 3, we are going to do an advanced dive into ancestral reconstruction and divergence time dating. As I said at the very beginning, phylogenetics is fundamentally a statistical representation of the data. So what we need to do is we need to introduce a couple of statistical models, including a likelihood and a Bayesian approach to phylogenetics. Time-calibrated trees rely on our ability to accurately estimate ancestral nodes and the rates of substitution, right? So if we want to actually use phylogenetics to date when two organisms diverge from each other, we need to be able to estimate this correctly. Furthermore, we're going to talk about how substitution rates act as priors that are applied in a Bayesian statistical framework. And we're going to explain what a prior is and how Bayesian statistics actually works. Okay, so how do we estimate ancestral sequences? So imagine we have some little hypothetical tree here, and we have our data. Our data represents the tips. For one specific location in a gene, we have an A, a T, and a C. Okay, now what we want to do is ask, what were the ancestral conditions for that specific location? Was it an A, was it a T, or was it a C? Which one is most likely given some model? As I said, a major component of divergence time dating is accurately estimating ancestral sequence. So we'll do this under a likelihood approach. Very often we do divergence time dating in a Bayesian approach, but we're going to start off with a likelihood because it's a component of Bayesian statistics, so we need to understand how it works. So a likelihood can be thought of as how likely it is that you got some data given a model of how that data was generated. As a very, very simple example, imagine I give you a list of numbers, okay? And I say, I got this list of numbers from rolling a dice. That's all the information I give you. So you want to say, okay, what model best explains that data? How can I explain how that data emerged? Well, if I think that that data emerged from rolling a 6-sided dice, right, then that is my model. And I'm going to ask, how likely is it that that data was generated, given that I think it was generated using a 6-sided dice? Now, if that data was actually generated using a 12-sided dice, then my model is really bad and it's not going to do a good job calculating that likelihood. Okay, then we can actually compare the 6-sided die to a 12-sided dice model and see which one is a better fit. But that's just to give you a kind of simple idea about how we would use a likelihood approach. So simplistically, likelihood equals the probability of the data, which is D, given some model. We're going to use theta as our indication of a model. Okay, so likelihood, probability of the data given the model. That little bar between them it means a conditional probability. So, and we say that as data given a model. Okay, so here's a likelihood example. So imagine you have the following nucleotide sequence. This is the sequence that you get. To calculate this sequence, what we might ask, or to calculate the likelihood of this sequence, what we might ask is, how likely are we to get this sequence given that it emerged completely by chance? Okay, so what would we need to do? First, we need to take the frequency of each one of the nucleotides in this data set. So we have 2 A's, 6 T's, 2 G's, and 2 C's. So how would we calculate this? Well, what we would do is we would multiply together every single one of those sites given the frequency of the nucleotides that we have across the data set. So the first site we know is an A. We know there are two A's total. So what we do is this first site is then 2 over 12, with 12 being the total number of sites we have. The second one is also an A, so it's 2 over 12 multiplied by the next frequency, the next, etc. That's how we build our likelihood. We can actually simplify this down instead of doing it across every single site by just raising them to exponents, right? So we're going to mash them all together, and we're going to take the frequency of A squared, frequency of T raised to the 6, because there's 6 possible T's, and that will just like condense our equation sum. We're then going to take the log likelihood. So the log likelihood makes it again a little bit more tractable, a little bit easier to deal with mathematically. If we remember how we can take log likelihoods, we just take the natural log of our entire sequence. So if we take the natural log of L, we take the natural log of pi sub A squared, which the way you do this is you just move the exponent to the front, then you take the natural log of the frequency. For the next one, we move the exponent to the front, take the natural log of the frequency, right? And we do that all the way across. Then we can plug in our numbers. So we have 2 natural log 2 over 12 plus 6 natural log 6 over 12, etc. And that gives us a log likelihood for this sequence of negative 14.9. So what does this number actually mean? In this context, it doesn't have a lot of meaning independent of anything else, right? We would use this number if we wanted to compare, for example, the likelihood that it arose by chance versus that it arose by some selection model, right? Then we could compare those two likelihoods and see which one was greater, right? But independently, without any source of comparison, the raw number itself doesn't have a lot of meaning. I just wanted to show you how we basically calculate that likelihood. Okay, so the next thing that we want to do is estimate what we call transition probabilities. So if we have some tip data that is, for example, a C, and we want to know how likely it is that the ancestor was a T. Well, there's a couple of things that determine this likelihood, right? Simplistically, if there was a great deal of time between the tip and the node, then the more time there has been, the greater the chance that that ancestral node was some sequence different than the tip, right? But if that ancestral node is very short or is very near the tip, then the probability is much greater that those two values are exactly the same, that it would be a C and the ancestor would also have a C. Okay, that's just to kind of prime your expectations on transition probabilities, but let's dig into one specific example. So let's ask, what's the probability that a T ancestrally changed to a C? Given that we expect that this is roughly approximated by a Poisson process, we can ask, what's the probability of there being no change at all? That's just equal to Euler's number, E raised to the negative mu T, where mu is the substitution rate, T is the amount of time separating them. And I've plotted this over here. So this is the probability of no substitution on the y and then time on the x. So notice that at very, very short time intervals, the probability of there being no substitution at all is very high, which means that it's most likely that those two sequences are exactly the same, right? Whereas the further and further and further you get, the probability that no change has happened gets lower and lower and lower and eventually goes to 0, virtually guaranteeing you that some substitution has occurred between two lineages. Okay, so if that's the probability of no change at all, the probability of at least one change is then just 1 minus that value. So let's assume the Jukes-Kantor 69 model for simplicity. I know I just went through this whole thing saying that most of the genome doesn't evolve this way, but when you see how the math ends up working out, if we did any more complicated model, the math just explodes, and it's really, really difficult to explain it simply in like a GTR model. So we're going to do it with the JC69 just so you can see how the math is derived, and then you can kind of think about what that math would look like if every single rate was independent, okay? So assuming the Jukes-Kantor 69 model for simplicity, the probability of any change to a C is 1 over 4, because C is 1 out of 4 possible nucleotides, so the probability of changing to a C is 1 out of 4. The probability of changing to a C, given that you started as a T, is 1 out of 4 multiplied by the probability of at least one change. Okay, that's 1 out of 4 multiplied by 1 minus E raised to the negative T. Okay, now recall that mu is the overall substitution rate, right? But what we want is the specific rate, and we're going to call this beta. And what we mean by the specific rate is the specific rate that a T changed to a C. Not that just any change happened at all, which is what we first derived down here, but that specifically it was a T that changed to a C, right? We need to be exact in what that ancestral sequence was. So beta then equals mu over 4, right? Because there's 1 out of 4 possible changes that represent a T to a C. So beta is mu over 4. We can rearrange this, and given that and to derive that mu is then equal to 4 times beta. What we can then do is substitute mu in our little equation down here. We're just going to replace mu with 4 beta. Okay, so this gives us a more exact way of asking, was it a T that then changed to a C? However, the astute observer will recognize that a T to a T isn't a substitution by definition. So it can't actually be mu over 4, right? Mu over 4 assumes any of the 4 possible changes, including a T changing to a T. But a T changing to a T is not a substitution, so we need to do a little bit more rewriting. So now let's rewrite this as V equals 3 out of 4 mu T. The 3 out of 4 represents the fact that only 3 out of 4 of the 4 possible changes represents a substitution, because 1 out of 4 doesn't represent a substitution. That's the T to T change. Therefore, we can rewrite this as 3 times beta T. Rearranging, we get V over 3 equals to beta T. Now what we're going to do is we're going to replace the beta T in our previous model with just V over 3. Doing that, we then get the actual estimate of the ancestral sequence. This is the real way we would do it. If we think that the ancestral sequence is a T, what's the probability that it turned to a C is 1 over 4, 1 minus e raised to the negative 4v over 3. That is the actual way in which we would calculate this, given that the Jukes-Cantor model is the model that we're going to assume substitution. Okay, now let's think how we would do this in a hypothetical tree. So this is our hypothetical tree where A, B, C, D, and E represent the name of the species. And then above each one of the species are just 3 nucleotides that represent each one of those species, okay? What we would want to do, how would we begin to calculate ancestral sequences? Well, first, we would pick the root of the tree, the V naught, right down here. This is the root of the tree, and we would just give some random sequence, okay? Apply a random sequence, and then we would go branch by branch, and we would calculate the probability of this, that the sequence across each branch is the same or different from that ancestral sequence. And I'm showing down here the probability that is the same versus the probability that that sequence has actually changed. Okay, so now let's take a specific example. Don't get too afraid by the math down here. I'm going to walk you through every single part of it, okay? Okay, so let's think about this as giving some ancestral node sequence. So we start off, we say this node is an A, all right? We say this node has an A, this one has an A, and this one has a C, all right? What's the probability that those nodes, that across each one of those branches, so across this V1 branch, that this started as an A and stayed as an A? What's the probability that this started as an A and along V2 changed to a C? Okay, so that's what we're going to be doing. That's how we're going to be estimating that probability. So now let's look at the likelihood. So the likelihood is then equal to 1 out of 4. That's our initial ancestral sequence. So we're starting off randomly at an A. We're saying A is our initial random pick. So 1 out of 4 possible choices multiplied by the probability that along the first branch, the V1 branch, there has been no change, right? Because we're saying that an A stayed as an A across this branch. Well, the probability that that happens is this here. And we're denoting this as V1 because this is V1. That's the rate across that branch that no change has happened at all. All right. Next, note that we put a C for this node. So what's the probability that we started as an A, but then across V2, we changed to a C? That's what this value represents. There's the V2. This is the probability that we actually changed. Now for V3, which is this branch here, this is an A. Now the node or the tip is an A. So then what V3 represents is the probability we started as an A and stayed as an A. That's, again, the same probability as in V1. And we just do this for each and every branch, given that we just assign some ancestral node value. We then put all this together, just like we did with the nucleotide sequences, and then we get the probabilities of changes, or of staying the same, I should say, raised to the 5th. There's 5 ways in which, across these branches, 5 branches in which no change occurred, and 3 in which change did occur. We then take the log likelihood of this value to make the math a little bit easier, and then that gives us the log likelihood for this particular tree, for this particular site, all right? Now what we have to do then is do this for all possible tree topologies and for all possible ancestral sequences. Then what we do is we take the most statistically supported tree as being the one that across all of those tree topologies, all of those ancestral reconstructions has the highest log likelihood. So as you can see, and what we just did was for literally one site, for one random iteration of that ancestral sequence. We have to do that for every possible ancestral sequence, for every possible tree topology, and iterate it over all. And then we compare which one of those iterations, which one of those different ones that we recreated gives us the highest log likelihood. And that's actually the one that we accept as the best explanation for the data itself. Okay, so that's the likelihood. That's taking a likelihood approach to estimating ancestral sequences and how we actually can pick out which one of the trees that we reconstruct across many bases. Again, that's one site. We have done this for the entire genome, 3.5 billion base pairs, right? So like it can explode. This analysis gets really big really quickly. Another way to do this is taking a Bayesian approach. So you've heard about Bayesian statistics, I'm sure, but who is this Bayes guy? What is Bayesian statistics actually all about? Well, now that we've gone through the likelihood, we need to recognize that most divergence time dating is done using a Bayesian approach. So now remember that the likelihood is the probability of the data given the model that we think generated that data, okay? What Bayes' theorem does is it actually rearranges this, and it rearranges this using the joint and marginal probabilities. I'm not going to go into how to actually derive the theorem. It's pretty trivial to actually do it, but we're just going to show you the results here. What Bayesian statistics fundamentally is doing is it's rearranging this probability statement. So instead of asking what's the probability of the data given the model, it asks what's the probability of our model given the data that it was generated under, okay? Now, given that we've had to rearrange the joint and the marginal probabilities, that gives us this value, the probability of the model given the data, and we call that the posterior probability, is then equal to the probability of the data given the model, we recognize this as the likelihood, multiplied by the probability of the model itself. The probability of the model itself is what we call the prior. All right, you can think about this very simplistically. What prior knowledge do we have about the reliability or the values or the estimations of that model itself? Okay, that's the prior. And then we divide this over what we call the marginal likelihood. The marginal likelihood represents all possible combinations of the prior and all possible parameter values of the likelihood. Okay, so this could be a very big number. We often this may be, if it's in discrete time, this is a summation. If it's in continuous time, as phylogenies often are estimated, then this is actually the integral over all possible parameter values of interest. Now, importantly, what Bayes' theorem allows us to do is estimate the actual parameters of the model. This is something that we don't generally do under a likelihood approach, though you can. It's just a little bit more of a roundabout way. Bayes' theorem allows a direct estimation of the posterior probability of each and every parameter of the model itself. An example of that parameter might be something like the substitution rate, right? So the rate that an A changes to a T. That's a parameter that you might want to estimate directly. And using a Bayesian approach, we can estimate that parameter exactly. Because again, we're estimating the probability of the model given the data, and so the data allows us to estimate the parameters of the model as opposed to us relying on the model being true and then conditioning on the data. Okay, but this leads to a pretty big problem, as you might have recognized from just like sort of the size of that marginal likelihood, right? So the pesky marginal likelihood explodes as we need to evaluate more and more parameters. Okay, so this is for a 3-parameter model. As you can see, that marginal likelihood is getting pretty big. We need to do a triple integral over each one of the different priors. Phylogenetics has many parameters, right? So remember that GTR model where each and every one of the changes was its own rate? That would mean we would need to integrate over every possible rate change. Not only that, but if we're putting any sort of hyperpriors, like if we're interested in like fossil calibrating a particular node that's a hyperprior that goes on top of that prior, that's an additional integration that we would need to do. So what happens is this marginal just explodes with more and more and more parameters of the model. And we generally want to add some additional parameters because we want our model to be as realistic as possible. We want to be able to account for variation across sites. We want to be able to account for variation through time. Like there's a lot of things we want to account for. We need to do that in the marginal. And this becomes computationally intractable. This marginal gets so big that we literally can't computationally estimate it. Even using supercomputers, it gets so big that it would take multiple lifetimes to be able to calculate it exactly. So how do we get around this problem? How do we actually deal with what we call this marginal bloat? And the way we do it is computationally. And I'm going to walk you through one of the most important statistical methods that is used in virtually all fields in which we want to be able to estimate some parameter of a model. Now, you may have heard of this before, you may not have heard of this, but what we're going to be talking about is a method that was put forward by Metropolis et al. In the 1950s, and it's called the Markov chain Monte Carlo. So the way this works is, let's say instead of trying to calculate all possible parameter space, we just say, let's pick some random number to begin with for each one of the parameters of our model. We pick some random number, right? And then that's where we start. We estimate the top part, so the likelihood and then each one of the priors, we estimate those given that random number. But then we make a second proposition. We take the second one here and we estimate each one of those parameters under just some second proposition. Now what we are interested in is the ratio of those two values. And what we want to know is which one of those has the greater value. And by doing this ratio, what actually happens is the marginal cancels out, right? We cancel out the marginal anytime that we do this ratio approach. So what we end up with is the probability of our first draw, of just like our first random draw, divided by our second random draw. And then we just do this again and again and again. This way, we are completely removing that bloated marginal likelihood when we're doing our estimation. However, this means that we need to make many propositions to try to converge on the best parameter estimates. If we could actually estimate the marginal likelihood, we wouldn't need to make a gazillion proposals to try to get to the best estimate. We would just get it directly. But since we can't estimate it directly because it gets so big, we cancel it out and we make a bunch of different proposals, okay? This is what a Markov chain Monte Carlo is doing. It's just making additional proposals, and since it's a ratio, it's dividing out that marginal likelihood, and then we just need to make a bunch of proposals. In a phylogenetic context, we make hundreds of millions of proposals, okay? We do this calculation hundreds of millions of times. So if that seems a little bit abstract, what I want to try to do is make it a little bit more concrete for you. So if your eyes are kind of glazing over looking at this math, we're going to make it very, very concrete. So let's imagine that you want to explore a landscape, okay? And in our example, the landscape represents parameter space, where some of the parameters in that space have higher likelihoods than others. And the way to think about this maybe topographically is there are valleys and there are hills and there are mountains, okay? And we have some robot, and we want this robot to explore this parameter space. But it does it randomly and it does it blindly. It doesn't know where it's going, right? It can't see anything. It's just stepping. And what we want that robot to do is climb to the highest peak on this landscape, assuming it can't see where that highest peak is. What we would need to do then is generate a set of rules that we would give to this robot and say, follow these rules. And if you follow these rules, you'll get to the highest peak, okay? So first, we say, take a step. That's the first one. And in our Bayesian thing, that's make a proposition, propose some new value for each of those parameters. Okay, takes a step. Now calculate the posterior of that proposal. Is the ratio of our new proposal divided by the old proposal greater than 1? If it is, that means our new proposal is better than what our old one was. In our landscape here, that means you took a step up. Okay, you made a climb in the landscape. Then you accept it. You accept that new proposal, you discard the old proposal, and you take the step. If, however, you make a new proposal and that ratio is less than 1, then you're walking down, right? You're going downhill. In that case, you reject the new proposal and you keep the old proposal and you don't take the step. Okay, so in doing this, every step that you take should eventually allow you to climb and climb and climb. What this leads to is this pattern of randomness initially as you're exploring the parameter space, and then eventually you reach a hill, you start climbing that hill, and then when you reach the peak, any new proposal that you could make brings you down the hill, right? So that you end up getting stuck and you stay at the peak of that hill. So what this looks like over time is that our little robot starts off really low on the landscape. We just plop him randomly on the landscape. The y-axis here is the posterior. So this is how good or how high up the cliff you're climbing or how good your estimate is. And then the x-axis is the number of steps you take. Steps are the number of proposals you're going to make. So he starts off really low. He's walking around the little landscape, and then he starts to climb, and then he reaches the peak. And when he reaches the peak, it flattens out, and he can't go anywhere else because any new proposal that he makes will move him down the hill. We do this many times. We do this with one robot, then we do this with 4, 5, 6, 10, 15, 20, however many robots it takes. And then we see, do each one of these, given that we started them randomly on the landscape, do they all find the same peak? Do they all what we call converge? Do they all converge on the same peak? If they do, this is really good evidence that we have found the highest posterior probability. And we did this, remember, without having to calculate that gigantic marginal likelihood. We were able to come to the right answer without needing to actually calculate this computationally intractable value. So if that seemed a little bit abstract, let's see if I can just really quickly kind of bring it back down to earth. So remember, what each one of these parameters represent is the substitution rate, ancestral sequences, all of those things that we calculated with the likelihood. We're having to calculate those things here as well, right? We're recalculating what is that likelihood of any given sequence, what's the likelihood of the branch lengths given those sequences. These are all the different parameters that we're estimating in this framework, okay? And we're trying to find the best one. And we're finding the best one by doing this stepping around the landscape approach, where the landscape represents the possibility of parameters. This also includes things like time of divergence. Like what's the most likely time of divergence given our data set and given our model. So it's in these little steps that it's taking is also trying to find how diverged backwards in time any two organisms might be. So just to try to bring this back to earth, because I know this might seem like it's getting a little abstract. Okay, so the other thing that we need to talk about here are priors and calibrations. So you'll remember that when I first introduced the Bayesian model, I called this little parameter here the prior. What the priors do is they guide the model. They allow it to explore parameter space in a guided sort of approach. The way you can think about this is imagine one of the parameters are the mutation rate. Okay, and we want to estimate the mutation rate. What we know is the mutation rate is not 1 out of 10, right? That would be an incredibly fast mutation rate that no organism ever shows. More likely, the mutation rate is like 1 out of 1,000 or 1 out of 1,000,000 or 1 out of several million, right? Like the mutation rate is some very, very small number. So what we don't want our model to be doing is spending a lot of time exploring parameter space that's irrelevant, that we know the rate is not actually that high, or it could be like looking at 1 out of 1,000,000,000. We know the rate is not that low. So there's a range in which the rate actually exists, and we want the model to spend most of the time there because we have some prior knowledge of what the rate should be, roughly what it should be. Now, that's not to say we're saying never look anywhere else. We're just trying to point it in the right direction to not spend a ton of time wasting resources exploring regions of parameter space that are irrelevant. Now, that's assuming we actually do have some prior information. Sometimes in phylogenetics, we actually have no prior information. We don't know, but we still need to give it some value. Anytime we have a parameter, we still need to provide a prior. In this case, we use what is called a uniform prior, where we basically just say between interval -infinity, +infinity, completely flat, uniform, explore the space. There's no constraint on any part of parameter space we could explore. That's a uniform prior. Again, generally with things like substitution rates, we give it some prior distribution that may be gamma distributed, maybe log normally distributed, etc., because we know that the parameter space is relatively narrow. Mutations aren't occurring incredibly quickly or just incredibly slowly, like 1 out of 1 billion. Fossil ages are also one of the things that we can use that are priors that we're using to calibrate the substitution rates, right? So like the age of a fossil, we would say is between 50 million and 100 million years. So 75 million as the mean with some variance around it. And maybe we think that variance is normally distributed. Okay. So then we would take that and we would plug that in as our prior. And so we're going to estimate ages for that node, given we think it occurs at a mean of 75 within some variance around it that's normally distributed. So the parameter space that our little robot is going to be searching is in that distribution. So that's priors and how we can use priors to calibrate specific ages. Okay, the last thing that we really need to talk about are molecular clock models. Very often you will hear creationists, and again, even non-creation, even a lot of like non-phylogeneticists will make statements like, oh, we assume a strict molecular clock. We very rarely ever assume a strict molecular clock. There are many different kinds of clocks, and I just want to introduce you to a couple of them here. So a strict molecular clock is this model up here. This is where you have one fixed rate, and then you can give some variance around that rate, but the rate itself is fixed, okay? And we assume that that rate applies equally to every single branch in the phylogeny. That's one kind of clock model. A second one, and one that's a little bit more commonly used, is the uncorrelated relaxed clock. What this does is it takes each one of those rates and it assumes that they're drawn from a shared distribution. So this is our phylogeny. Each one of the rates are different. They're uncorrelated to each other, but the value of that rate is drawn from a shared distribution. This is like a log normal distribution. Each one of these little points represents the value that it's drawn from. So what this allows is that rate can change, right? The rate can change and there's no correlation between rates across each one of the different branches. It's just drawn from a shared distribution. One of the most complicated ones is actually the random local clock. So the random local clock is this one here. It assumes that each one of the rates represents a mean of a distribution of rates across that branch, and that distribution of rates can be passed on to descendant branches, or with some probability, that distribution can completely change in descendant branches. So for example, these two are completely different, right? They represent distributions that are not shared, whereas this distribution and this one is passed on, right? That's a directly inherited branch. Now, that's not to say that the rate itself is exactly inherited. It just means that the distribution upon which the value is drawn is inherited across branches. Okay, let's put it all together now. We've gone through 3 different tiers, 3 different ways in which of presenting how phylogenetics works. Let's summarize this 3rd tier. I know it was like really abstract. There was a lot of math, a lot of statistics. Hopefully you got sort of the general gist, but let's summarize it all up here. So first, we generate some random tree. We just put together some random tree given our tips. We propose an ancestral sequence for each one of the nodes in the tree, and then we calculate the probability of that sequence given our model. And our model includes substitution rates, fossil calibrations, clock models, all of those sorts of things are in our model. Now remember, in a Bayesian approach, we can estimate each one of those things independently. So we're estimating the parameters of the model while we are simultaneously estimating the tree. And then we repeat this process literally millions and millions of times until we find that tree that has the highest probability. This includes the topology, the branch links, all of the rate parameters, all of those things represent millions of iterations on these processes until we get the best possible one, okay? I think I've shown pretty clearly that phylogenies are not just lines on paper, right? They are a statistical representation of the data itself. Now, any creationist watching this might point out that, for example, in our likelihood, we are saying that there's the probability of the data given a model, okay? What if that model is wrong? To them, the model is what is wrong. And so whatever it is that we're reconstructing is incorrect because we're assuming the wrong model. In much the same way that I said before, that if you have a list of numbers and you're assuming your model as a 6-sided dice, but really a 12-sided dice is what explains how that data emerged, you're going to get the wrong answer. Well, we can directly compare the likelihood of two competing models. This is what we do in statistics. This is literally just basic statistical model comparison. So let's say we have two models. We have theta 1 and theta 2. These are the two models. So we can calculate the likelihood of the data given it arose under one model. We can calculate the likelihood of the data given it arose under a different model and compare those likelihoods. So if the likelihood of one is greater than the other, so if L1 is greater than L2, then theta 1, that model better explains that data. Alternatively, if theta 2 is the better explanation, then we just reverse it. There's also the possibility that each one of these models are indistinguishable from each other, that they produce equivalent likelihoods. You might say that they're non-discriminant or they're indistinguishable, okay? So these are the three possibilities of competing models. So which model better explains the data? If we think about it as our model, the model of phylogenetics is that the data emerged under a tree-like structure, right? That there is a tree structure that connects the data, whereas creationists would argue that there is no tree structure that connects the data, that instead all of this data emerged via independent origins, okay? Well, this has been directly estimated. So Theobald in 2010 compared an independent origins model to a common descent model, and exactly this kind of likelihood approach. This is the approach that he used comparing these two models. What he found was that the common descent model, that all of life has a universal common ancestor, was 10 to the 2,860 times more likely than an independent origins model. What that means, right, is that likelihood that the data emerged under a common descent model is that many times more likely than that it emerged under an independent origins model. So this gives us a direct statistical comparison of two models, two competing models, using the exact same likelihood approach that we used to understand how phylogenies are built. Okay, so just to recap, we went through three different tiers of how to construct phylogenies. We started off very simply with just sort of a primer on how to construct them and how divergence times are estimated. We then took a bit more of an advanced view, looking at substitution models and fossil calibrations, and we talked about how to overcome some of the assumptions of our simple model. And then finally, we gave the statistical way in which we actually reconstruct phylogenies from both a likelihood and a Bayesian approach. Collectively, I think these overwhelmingly show that phylogenies are not just lines on paper. They are statistical representations of the data given models. And these models can be compared statistically as well, including models that may be of independent origin versus common descent, in which common descent overwhelmingly better explains how that data emerged than independent origins. So phylogenies are not just lines on paper. Thanks so much for being here. If you have any questions, please feel free to drop them in the comments. Let me know what you thought about this sort of three-tiered approach. If by the time we got to 3, you just sort of tuned out. And maybe I'll think about iterating on this in the future, but I thought it might be helpful to sort of break it into different levels of complexity. Just kind of maybe build up to the most complex. So let me know what you thought about that. Again, thanks so much for being here, and I will catch you next time.